Men and women have always looked to the clouds with wonder. We've also looked to the clouds for clues about the weather. Weather and climate have always had direct and sometimes cataclysmic impacts on our lives. In its relatively brief geologic history, the Earth has gone through many climate cycles which have had profound effects on all life forms. It wasn't until the Industrial Revolution of the 19th century, though, that human presence began to truly accelerate its impact on the global environment. Today, scientists around the world are trying to discover the extent to which human presence has affected the global environment. The Atmospheric Radiation Measurement, or ARM program, is the U.S. Department of Energy's major contribution to the overall U.S. Global Change Research Program. Since the onset of the Industrial Revolution and subsequent population explosion, we have seen dramatic growth in agricultural activities, economic development, and manufacturing. Unfortunately, we've also seen a concurrent dramatic increase in pollution, especially air pollution. Factories, internal combustion engines, power generation plants, and even farm animals are continually spewing particulates, aerosols, and gases into the air. Since the 18th century, for example, it is estimated that the levels of carbon dioxide in the atmosphere have increased by 30%. In 1978, the U.S. Department of Energy initiated the Carbon Dioxide Research Program and has reported annually to address the effects of increased concentrations of carbon dioxide in the atmosphere. Since then, the Department of Energy research programs have made significant progress toward understanding the potential impact of energy usage on the Earth's environment. More recently, the Department of Energy has developed programs that are an integral part of the extensive national and international effort to understand global climate change. Large-scale numerical models are key elements of modern climate research and the effort to accurately predict future climate. The models of the global climate system have advanced to include realistic geography, the annual cycle of the seasons, and varying cloud cover. But research has also revealed that important uncertainties remain in these computer models. The Atmospheric Radiation Measurement Program was created in 1989 to address one of the most important of these uncertainties: clouds.
The scientific goals of the Atmospheric Radiation Measurement Program are to provide the data and the understanding necessary to improve critical parts of climate models. Basically, the ARM program is a little bit like an automobile body shop and engine repair. We are a place where you can go in and test the individual components of climate models, particularly those related to how energy is deposited in the atmosphere, how much energy from the sun makes it to the surface, and the set of processes that take place. So we can basically take apart a climate model, physics component by physics component, test those individually, put them back into the climate model, and see what the effect is in our ability to be able to predict.
Modeling the impact of clouds is difficult because of their complex and differing effects on weather and climate. Clouds can reflect incoming sunlight and therefore contribute to cooling, but they also absorb infrared radiation leaving the Earth and contribute to warming. High cirrus clouds, for example, may have the impact of warming the atmosphere. Low-lying stratus clouds, which are frequently found over oceans, can contribute to cooling. In order to successfully model and predict climate, we must be able to both describe the effects of clouds in the current climate and then predict the complex chain of events which might modify the distribution and properties of clouds in an altered climate. It is not a simple task. The treatment in general circulation models of clouds and their interaction with solar and terrestrial radiation required a new scientific approach in the study of general circulation models. ARM has chosen to create an experimental framework called a Cloud and Radiation Testbed, or CART site, in which large arrays of instruments can be used over extended periods of time to understand not only the processes associated with clouds and radiation, but also to evaluate how well these processes are captured in climate models.